Good day, everyone. Today we will discuss the joint probability distribution. Okay? So, under the joint probability distribution, we have contents here in this slide. Okay? So, in this lesson, we will discuss three major topics. Okay? So, first we will discuss the basic one. So, we have the joint probability distribution. Okay? After that, we will discuss the marginal probability distribution. And lastly, we will discuss the conditional probability distribution wherein the Bayes theorem or Bayes theorem is present. So in this conditional probability distribution, we will also discuss the Bayes theorem or the Bayes theorem. Okay? So we will discuss these three topics in this lesson now. Okay? So in module number 2.1, we studied probability distribution for a single random variable. However, it is often useful to have more than one variable defined in a random experiment. So always remember, in terms of joint probability experiment or joint probability distribution, we are dealing with two or more variables. So we have two or more variables. Okay? In terms of discrete, okay, I mean in terms of joint, we have two or more probability or variables. Okay? So for example, in the classification of transmitted and received signals, each signal can be classified as high, medium, or low quality. We might define the random variable x to be the number of high quality signals received and the random variable y to be the number of low quality signals received. Okay? So in this case, in terms of joint probability distribution, okay? So we have two variables present, okay? So we have the variable x and the variable y, okay? It can be interchangeable or it can be changed, but in terms of joint probability distribution, the common letters or the common variables used in terms to denote a certain variable, okay, or a certain amount is the variable x, okay? The variable x and the variable y, okay? So in the another example, in the continuous random variable x can denote the length of one dimension of an injection molded part, and the continuous random variable y might denote the length of another dimension. We might be interested in probabilities that can be expressed in terms of both, like I said, x and y. Again, in terms of joint probability distribution, okay, we are dealing with probability of the events happening simultaneously, meaning the events are happening at the same time. Okay, therefore, if there are two or more events, automatic we have two or more variables. In our case, in this example, okay, we have two variables wherein it is denoted as our variable x and our variable y. Okay, remember that. So if the specifications for x, for example, is 2.95 to 3.7505 and y is 7.6 to 7.8, we might be interested in the probability that a part satisfies both specifications. So you have this range. So if x and y are two random variables, the probability distribution that defines their simultaneous behavior, or it means simultaneous happening at the same time, is called a joint probability distribution. Okay? So, the joint probability distribution is defined as or can be represented as this condition. So, we have the f of xy sub f xy is equal to probability of x is equal to small x, y is equal to y. So, that's how we represent a certain joint probability distribution. Okay? So here are some rules or guides on how we can remember or what is the value of different instances in terms of joint probability distribution. Okay? So we have three conditions here. So the joint probability mass function of the discrete random variable x and y denoted as f xy sub f xy. So satisfies. So always remember that all x and y or all the probability should be what? Non-negative. Okay? So it should be what? Greater or equal to 0. Okay? Number 2. The probabilities of all possible combinations of x and y within the range add up to 1. So like I said, in terms of probability, okay, the sum of all probability should be equal to 1. Okay, and lastly, number 3, the probability of p. Okay, the probability of x is equal to x, y is equal to y is defined by the function of x and y at point xy. So here's the representation once again. Okay, so for the density function, not so important. So let's just remember the rule. So it should be a non-negative. The area or the total area or the total probability should be equal to 1, and also the representation here in number 3. Okay, so examples of joint probability distributions. So we have the number x of hours watching TV as related to the y number of hours spent exercising. So if we look closely in some examples, okay, we are dealing with two or more variables wherein they are happening at the same time. Okay, again, next, x number of pages on a report and y grade given by teacher. So next, x minutes spent on a sports activity and y number of blisters created. And lastly, you have x hours spent at studying and y grade of student in that course. Okay, so that's so these are the following simple examples about joint probability distribution. So we have two random variables, so we have x and y present. Okay, so another one in terms of table method, or we have this distribution here in our screen. So calls are made to check the airline schedule at your departure city. You monitor the number of bars of signal strength on your cell phone and the number of times you have to state the name of your departure city before the voice system recognizes the name. So in terms of joint probability distribution, we tend to let x and y. Okay, therefore we can denote a certain amount or a certain number in terms of x and y. Okay, so in our case, in this example, so our let x, okay, here. So our x, so denote the number of bars of signal strength on your cell phone. And our y here is the denote the number of times you needed to state your departure city. Okay, so that's how we represent or make a tabular table in terms of joint distribution, joint probability distribution. Okay, so this is just a representation of what this question is all about. Okay, so always remember, in terms of joint probability distribution, we are dealing with two or more variables wherein x and y is always used as a basis in order for us to denote a certain amount of variable. Okay? So example number 3. So now it will be a solving problem. So a coffee shop sells two sizes of lattes. Okay? So the two sizes are, so we have the small and large. So let x be the random variable representing the number of small lattes. Okay? So our x, okay, is for the small lattes. Okay? And y be the random variable representing the number of large lattes. So our y is large lattes. So the joint probability distribution of x and y is given in the table below. So we have this table wherein we have x. So our x is for the small lattes, okay, and our y is for the large lattes. Okay, so we have here different values. So these are probabilities wherein this can be equal to what? 10%, 20%, 5%, 15%, 25%, 0.10%, 10%, I mean, 5%, 10%, and 0. Okay? So here are the questions. Letter A. What is the probability that the coffee shop sells exactly one small latte and one large latte in an hour? Okay. Letter B. What is the probability that the coffee shop sells at least one small latte in an hour? And lastly, letter C, what is the probability that the coffee shop sells a total of 2 lattes in an hour? Okay? So let's solve this problem. So solution A, for solution A, so what is the probability of one small latte and one large latte? So this is given directly in the table where x is 1 and y is 1. So let's look at the table wherein we need to find a certain intersection wherein x is 1 and y is 1. So if you look closely, so here is the x1 row, okay? So in terms of x1 row, okay, so we need to find the intersection of x1 and y. So in this case, the intersection of x1 and y1 is 0.25 because, okay, 0.25 is in row x is equal 1 and it is in column y is equal to 1. Therefore, the value of our probability of one small latte and one large latte is equal to 0.25. Okay, so we have here 0.25. Okay, solution letter B. So what is the probability of at least one latte? Okay, so in order for us to solve this problem, we need to find different combinations wherein there is at least one small latte. Okay, so in terms of small latte, okay, so we have here this condition. So let me just erase this one. Okay, so in terms of small latte, it is uh, uh, denoted as x, wherein we need to find a certain combination wherein it is at least one latte. So what are the different combination that we need, or what are different intersections that we need to consider? Okay, so let's look at this table. So it is said in the problem, so what is the probability that the coffee shop sells at least one small latte? So let's look at x is equal to 1 because x denotes what? The small latte. Okay, so what are the values under x is equal to 1? So we have 0.2, 0.5, 0.25, 0.1, 0.05, 0.1, and 0. Okay, because we are talking about at least one small latte. Therefore, x is equal to 2 is also included because it is greater than the least one or the minimum, which is equal to 1. Okay? So all we need to do is we need to add all the probability. So we have 0.2. Okay? So we have 0.2 plus 0.25 plus 0.1 plus 0.05 plus 0.1 plus 0. So if we sum it up, we have 0.7 or we have 0.70 as our probability of at least one latte. Okay, so if you look closely, in order for us to solve this problem, we just need to establish a table and we need to examine the said table. Okay, let's erase this. So next, letter C. What is the probability that a coffee shop sells a total of 2 lattes in an hour? So we need to find the total probability wherein, okay, the coffee shop will sell 2 lattes in an hour. So what are the following parameters that falls under 2 lattes? Okay, so let's look at the table again. Okay, so what are the parameters or rows or column in terms of x and y that has two what? Two values. Okay, so we have x is equal to 2 and we have y is equal to 2, wherein the values are the following. So we have 0.05, 0.10, 0.1, and 0.05. Okay. Okay. So let me just correct this. Okay, so typographical error. So it means in the problem is we need to find coffee shop sells a total of 2 lattes. Okay, so what are the parameters? So we have 2, 0, okay, we have 1, 1, and we have 2 and 0. Okay, so what are the values here? Okay, so first we have 2 and 0, so we have 0.05, okay, here. Next, we have 1 and 1, so we have 0.25. And we have 2 and 0, therefore we have 0.05. Is it correct? Okay. So the total number is equal to 0.35. Okay. So that's how we solve this letter C. Okay. So disregard the first equation that I taught. Okay. So let's just follow this format. Okay. So in order for us to get the total lattice, we just need to get what? X is equal to 2, y is equal to 0, okay, x is equal to 1, y is equal to 1, and lastly, x is equal to 0, y is equal to 2. Because we need a total of 2 lattice. So 2 plus 0, we have 2. 1 plus 1, we have 2. 0 plus 2, we have 2. Okay? Remember that. Example number 4. Imagine you have a bag with 4 marbles. So it has 2 red and 2 blue. You pick 2 marbles out of the bag without replacement. Okay. So here's the rewards. So first is create the joint probability distribution for x and y. And number 2, what is the probability of picking exactly 1 red marble and 1 blue marble? And number 3, what is the probability of picking at least 1 red marble? Okay? Like I said earlier, in terms of joint probability distribution, we tend to let x and y. Okay? So in this case, let x be the random variable representing the number of red marbles, and let y be the random variable representing the number of blue marbles. Okay? So here are the possible outcomes that we can encounter. So in terms of picking 2 marbles, we can have RR or red red. Next we can have RB or red blue. Next we can have BR or blue red. Excuse me. And lastly we can have BB or we have blue blue. Okay? So in terms of representation, okay, so let's relate in this problem. So the first, if you pick 2 reds, okay, therefore you have x is equal to 2, y is equal to 0. We're in, okay, again, we let x for red marbles, okay, and we let y for blue marbles. So that's how this condition or this representation is made. Okay, next, red blue. So our x is 1, our y is 1 because we have 1 of each. Okay, next, BR, we have x is 1, y is 1, again 1 of each, and blue blue or BB, so we have 0 as x and 2 as our y because we have 2 blues. Again, y represents the blue marbles. Okay, so we have this condition. Okay, so next is to calculate the probabilities for each outcome. Okay, so how we came up with this solution. Okay, so let me just explain this term. Okay, so in order for us to get this answer, okay, so remember the multiplication rule number 2. Okay, so if you remember the multiplication rule number 2, so if you pick a certain thing, like picking a marble or picking red balls or colored balls or picking a card, if there is an instance that it is not replaced, therefore the possibilities in the second one will be less than 1. Okay? So in this case, if you have 2 is equal over 4, for example, you pick a certain red marble, therefore, the possibilities, okay, will be less than 1. So 2 over 4, so 1 minus 2 minus 1, 4 minus 1. So we have 1/3. So you just need to multiply it. You have 1 over 6. The probability next is red blue. Okay. So you pick up a certain ball and you have 2 blues. So you have 3. Okay. So let's just follow the trend. Okay. So you just need to what? Subtract 1 to its denominator. Okay. It depends on the situation. Okay. So after we computed this type of value, so we can represent it in a table. Okay? So like I said, our x is for the red marbles and our y is for the blue marbles. We're in. We have this conditions. Okay? So solution number 2, what's the question? What is the probability of picking exactly one red marble and one blue marble? So let's look at the table. So what is the intersection value that intersects with x is equal to 1 and y is equal to 1? So we have here 2 over 3 as our answer. So that's how easy you answer or solve a certain joint probability distribution. First step is you need to determine the probability. Second one is to make a joint probability distribution table. And after that, you just need to what? You need to examine the table in order for you to get the answer. So what are the values intersect in terms of x and y? Okay? So required number 3, what is the probability of picking at least one red marble? So in terms of this, so we need to find a certain numbers, okay, that is the numbers that are at least one red marble. We are under in this row. So this x0 is excluded because, okay, it has no values of marble. So what are the values, okay, that fall under the x1 and x2? Because we have at least one red marble. Therefore, x is equal to is already included or also included because it is more than, again, with the minimum is equal to 1 because 1 is the at least number. Okay? So what are the values that under x1 and x2? So we have 0 plus 2 thirds plus 0 plus 1 over 6 plus 0 plus 0. So let's cancel the zeros. So we have 2 thirds plus 1 over 6. Therefore, we have 5 over 6. So that's how you determine a certain intersection or certain value in terms of different rewards about joint probability distribution. Okay? Next, after we discuss the joint probability distribution, we will now discuss the marginal probability distribution. Okay? Wherein, in terms of marginal probability distribution, okay, the probability of a single event occurring independent of other events. So, if more than one random variable is defined in a random experiment, it is important to distinguish between the joint probability distribution of x and y and the probability distribution of each variable individually. The individual probability distribution of a random variable is referred to as its marginal probability distribution. So for example, consider discrete random variables x and y. To determine, we sum up p is equal to x, probability of x is equal to x, y is equal to y, over all points in the range of x and y for which x is equal to x. Okay. One thing that you need to remember in terms of marginal probability distribution, okay? So problems under marginal probability distribution, okay? All you need to do is to get the sum. Okay? In terms of marginal probability distribution, all you need to do is to get the sum of probability based on different conditions. Again, in terms of marginal probability distribution, so problems under marginal probability distribution, all you need to do is to get the sum of probabilities given in the table based on different rewards and condition. Okay? It is just the sum of the probabilities. Okay? Remember that. So here's the formula. Good to remember. So example number 5. So similar to the given table from example number 2, evaluate the marginal probability distribution of x and y. So if we have this example that f of x is equal to 3, wherein our probability, okay, should have what? At least 3. Okay, so the probability is less than 3. Okay, wherein the x should be at least is equal to 3. So what are the values with x is equal to 3? Okay, so we have here, so we have x, therefore the values under in this column. Okay, so if we have x is equal to 3. Okay, so here's the values. So we have x3 y1. Okay, so we have x3 y2, x3 y3, x3 y4. So we have 0.25 plus zero point 0.2 plus 0.05 plus 0.05. So we have 0.55. Like I said earlier, in terms of marginal probability distribution, okay, we are dealing with the sum of probabilities in terms of different conditions. So in this condition, okay, the required is we need to find the marginal probability distribution or the totality of certain condition wherein the x should be at least equal to 3. So it depends on the given, and it also depends on the required that the problem will present. Okay? So example number 6. A small coffee shop sells two sizes of coffee. So we have small for S and large for L. And two types of coffee. So we have regular for R and decaf for D. So the following table shows the joint probabilities of the coffee size and type a customer orders. So here's the rewards. So what is the probability that the customer orders a small coffee? And number 2, so what is the probability the customer orders a regular coffee? So in terms of solution number 1 is we need to find the total probability of a customer will order a coffee. So in order for us to get the probability or the total probability, so we just need to add the probability of S and R. We have the probability of S and R and the probability of S and D because they intersect to each other. So what is the value? So in terms of PSR, P, S and R, so we have zero point 0.3 here. And in terms of P, S and D, so we have zero point 0.2. So we just need to add, like I said, it is just the sum of the probabilities based on the condition. So we have 0.3 plus 0.2, so we have 0.5. Okay? So number 2, so what is the probability that the customer orders a regular coffee? So in terms of regular, so we just need to look for the regular column. So what is the value under the regular column? So we have small regular and we have large regular. Wherein we just need to add these two values. Therefore, we have 0.3 plus 0.4. We have 0.7. So that's how simple to solve a certain marginal distribution or marginal probability distribution. Okay? So you just need to find the sum of the probabilities. Okay? Okay? Next, we have example number 7. So, a survey was conducted on the types of pets owned by people in a certain neighborhood. So, the results are summarized in the following table, which shows the joint distribution of dogs as D and cats as C. Okay. So, we have this representation. So, our D is dog. So, owns a dog is D. So, doesn't owns a dog. So, we have the symbol here, dash D. Okay. So, our C is owns a cat and doesn't owns a cat is dash C. Okay. So, find the marginal probabilities of the following. So, we have P is equal to D, P, PD. So, we have P dash D, PC, and P dash C. So, what are the probabilities in terms of PD? Okay. So, what are the values under the PD? So, all we need to do is we need to add the values. Okay. So, we have 0.25 plus 0.15. Therefore, we have 0.4. Okay. So, in terms of doesn't own a dog, so we just need to add it. So, we have 0.3 plus 0.3. So, we have 0.6. Next, in PC, okay, so we just need to add the values here. So, we have 0.25 plus 0.3. Therefore, we have 0.55. Next, we have PC, P dash C, I mean. So, all we need to do is we need to add 0.15 plus 0.3. So, we have 0.45 here. Okay. So, notice that PD plus P dash D is equal to 1 and PC plus P dash E is equal to 1 as expected. Because based on the rules of joint probability distribution, the probabilities, okay, should be equal to, or the sum of all probability should be equal to 1. So if you look closely in this table, the sum or the total number of probabilities is equal to 1. Okay? Again, in terms of marginal probability distribution, we are dealing with the sum of the probabilities based on different rewards. Okay? So in our case, we need to find the probability of D, or the marginal probability of P, D dash D, C, and dash C. Okay? So that's how simple it is. Okay? So last is we have the conditional probability distribution. So when two random variables are defined in a random experiment, knowledge of one can change the probabilities that we associate with the values of other. Okay? So in terms of conditional probability, so the possibility of an event happening based on the existence of a previous event or outcome. So in this case, so it's more like the multiplication rule number 2, wherein we have dependent variables. Okay? So let's have an example here. Okay. So imagine you have a bag of marbles. Okay. So there are 10 marbles in total. Okay. So we have 5 red. Okay. We have 3 blue. And we have 2 green. So we have 10 total. Okay. So what is the probability that the first marble you pick is red and the second marble you pick is blue? Okay. So let's first have the number one solution. So first is we need to get the probability of picking a red marble first. So there are 5 marbles out of 10 marbles. So the probability of picking a certain red marble is 5 over 10, or we have 1 over 2. So we have the answer for the first question. So the second question, the probability of picking a blue marble given that a red marble was picked first. Therefore, after picking one red marble, there are only 9 total marbles left. Out of those 9 marbles, 3 are blue. So the probability of picking a blue marble second, given that a red marble was picked, therefore it is not replaced, is equal to 3 over 9. Because 3 is the available blue marbles and 9 is the available total marbles after you pick a certain red marble. Therefore, we can simplify it as 1 over 3. So, like I said, in terms of conditional, to get the probability of both events happening, multiplication rule, we multiply the probabilities together. So, we have 1 over 2 multiplied by 1 over 3. Therefore, we have 1 over 6 as our answer. So, that's how we compute a certain conditional. So, conditional is like more likely like joint, but it depends on the condition. Okay? So lastly is we have the Bayes theorem. Okay, so Bayes theorem is used under the condition of conditional probability. Okay, so let's start this. So Bayes theorem defines the probability of occurrence of an event associated with any condition. It is considered for the case of conditional probability. Also, this is known as the formula for the likelihood of causes. Okay, so the formula for Bayes theorem is we have the probability of A or B is equal to probability of BA or AB or B or A multiplied by probability of A divided all over by probability of B. So how we can apply this in a problem? So let's have this example. Okay, so in a neighborhood, 90% of children were falling sick due to flu and 10% due to measles and no other disease. Okay, so the probability of observing rashes for measles is 0.95 and the flu is 0.08. If a child develops rashes, okay, find the child's probability of having a flu. Okay, so we need to find a certain probability wherein a child can have a rashes and having a flu at the same time. Okay, so our let F is the children with flu. Okay, wherein let M is the children with measles. Okay, and let R is children showing the symptom of rash. Okay, so the probability of children with flu, so we have 90% here. Okay, so it is equal to 0.9. The probability of children with measles is 10%, so it is equal to 0.1. Okay, and the probability of children, okay, the probability of observing rashes for measles, okay, so and for flu is 0.95. Okay, and the probability for flu, so sorry, for the partnered of rashes and measles, rashes for measles, we have 0.95, and we have rashes for flu is we have 0.8. Okay, so is it clear? So it is partnered rashes and flu, partnered rashes and measles. Okay, so in order for us to solve for the probability of a certain children that has a flu, okay, having flu, okay, so we have this formula. So we can relate this formula. So we have probability RF multiplied by PF divided by probability RM multiplied by PM plus probability of RF multiplied by probability of F. So substitute the values. We have 0.08 multiplied by 0.9 all over 0.95 multiplied by 0.1 plus quantity 0.8 plus multiplied by 0.9. 0.08 multiplied by 0.9. So we have this final answer of 0.43. Okay, so that's how we relate a certain problem. Okay, so just look for the combinations here, okay, and look for the independent variables. Okay, so in our case, the independent variables are PF and PM. Okay, and the combination variables is we have the RF and RM. So that's how you will solve a certain problem. And if you look closely here, okay, so we have partnered here. So if it is in M, it is also M here. So if it is F here, it is also F here. In order for us to what? Cancel it out. Okay? Okay. So that's the end of our lesson for module 2.3. So it's just a short solving lesson. So I hope everyone learned. So if you have questions and clarifications, just message me in Teams. And if you have other inputs or other questions, don't hesitate to message me. Okay? So I hope everyone will learn in this recording or this lesson. And let's meet next week. Okay? So this week we will have another topic. So we will have our module 2.4 in your next class or next meeting asynchronous again because we have this celebration of our foundation week. Okay, so thank you for everyone. I hope you learned something and apply this in your daily life. Thank you everyone and have a good day.